All right, so how can we better show covalent bonds? We're going to do so with what's called a Lewis structure, which is going to show the atoms that are part of that covalent compound and the bonds that hold them together. This is going to lead to conclusions about the shape of the molecules, branching that's there. It's really going to describe the shape of a molecule, which again could take up a variety of forms, unlike ionic compounds, which as we saw is really just matching up and forming a checkerboard with those specific ions. In our Lewis structure, valence electrons are going to be shown as dots. Shared pair electrons, which is a covalent bond, are going to be shown as lines between atoms. So again, lines, that's our covalent bond. Dots, those are extra lone pair electrons. And again, for this course, the goal is not to be able to predict complicated Lewis structures, but just to visualize how atoms are able to share electrons, form covalent bonds, and make discrete molecular packages. And so let's look at the simplest example. We start with hydrogen. Hydrogen, which has one valence electron, we can draw a Lewis structure of just that hydrogen, which is an H, that's hydrogen, with one dot, that's its one valence electron. But this isn't really happy yet because it's just one hydrogen atom and it wants to have 2 electrons. Remember, hydrogen wants 2, almost everything else wants 8. Hydrogen's so small that it really just wants 2. But with another hydrogen, they can do this. They come together and they each share their 1 electron so that each of them feels like it has 2 electrons. And this feeling like it has 2 electrons and the sharing of electrons makes a covalent bond, which we draw below H with a line to another H. And this is the Lewis structure for hydrogen gas, H2. Both hydrogens now are feeling like they have 2 electrons and we have a stable molecule. Okay, what about water? This is the most important molecule that we're going to study this semester. We're going to talk quite a bit about it in this module. Oxygen has 6 valence electrons, and we can start with this oxygen depiction where we have an oxygen in the middle, 2, 2, 1, 1. If we want to do them individually and then paired up as we get to 8. And remember that oxygen wants to have 8 electrons total. Let's remember our hydrogen atom. It's got 1 valence electron and it looks like this, right? H with 1 dot. The oxygen alone is not stable. The hydrogen alone is not stable. And remember here that when making water, we have 2 of these hydrogens. They each want 1 more electron. We have 1 oxygen. It wants 2 more electrons. And we know this because of the valence electrons it has, which we know from the location on the periodic table. Oxygen, therefore, is going to share 1 electron with each hydrogen. So one of its lone electrons makes a bond with 1 hydrogen, the other makes a bond with the other. And if we look at this now complete structure of water, the first hydrogen has 2 electrons that it feels like it owns from the covalent bond. Oxygen has 8. It's got 2 from the one covalent bond, 2 from the other covalent bond, and then 2 plus 2 is 4 lone pair electrons that are all its own. Those are the dots, so 8. And the other hydrogen also has 2. And this gives us water, which is a nice stable molecule. Okay, to emphasize this picture of water, 2 types of electron pairs, and electrons really do like to live in pairs, whether they're in a covalent bond and paired, or they are all by themselves and they want to be paired. And so the bonding pairs are the covalent bonds. These are the lines. These are one atom's electrons sharing with another atom's electrons. The lone pairs or the non-bonding pairs are kind of like the leftovers on oxygen, right? It came with 6, it wanted to share 2, but 4 of them it's keeping all to itself. These still take space around the atom. They do not participate in bonding, but they do still count on the oxygen towards its octet and are very important to make as part of our Lewis structure. If we look at oxygen gas, this starts to get into more Lewis structure details because remember oxygen O2 is another molecule we know. And this is kind of the idea. It's not that we can just take any collection of elements and make a molecule. It's that we know what the formula for molecules are. Lewis structures are theories on what's most stable to show their shape. So we know that oxygen gas exists, right? That's kind of not up for debate here. We know oxygen has 6 valence electrons. How do we theorize why O2 is stable and what it may look like using some sort of a Lewis structure depiction? And remember that oxygen wants to form 2 bonds If there's two oxygens, they both want to form two bonds because they both want two more electrons, and they do by making a double covalent bond. This double covalent bond comes from each of the oxygens sharing two electrons. First electron they share bond 1, second electron bond 2, double covalent bond. And finally we have carbon dioxide. Carbon has 4 valence electrons, and this number 4 is really, really important to remember for carbon. Carbon wants to make 4 bonds because it's got 4 valence electrons and it wants 4 more. Because of this, a lot of the branching and the structure of molecules is determined by carbon in biochemistry in our biology. So this idea of carbon has 4 valence electrons, therefore wants to make 4 bonds, very essential. Oxygen still has 6, still wants 2. Because carbon wants to make 4, it can make 2 bonds with one oxygen, 2 bonds with the other, and we form CO2 here, which has an oxygen with 2 lone pairs and a double bond to a carbon, which is double bonded to a second oxygen that also has its 2 lone pairs. The oxygens have access to 8. They feel like they have 8 electrons. The carbon feels like it has 8 electrons, and everyone is happy. Okay, so as kind of a, not a cheat sheet, but a shortcut here, when we're looking at the octet rule, we're going to see some similar patterns, right? Because we're trying to get to 8 total electrons. So carbon has 4 valence electrons, and it wants to make 4 bonds in order to get to 8. Because in every bond that it forms, it's like it gets to feel that it has 1 more electron. And when it uses its 4 electrons to make 4 bonds, it gets to its 8, and it has none left for itself. This is just the general picture of what carbon likes to do 99% of the time. Nitrogen is one up from carbon on the periodic table. It's got 5 valence electrons. And because it's got 5, it wants to form 3 bonds. When it forms 3 bonds, it's going to have 2 electrons left behind, and so 1 remaining lone pair. And so, this chart can be really useful for predicting the bonds that are formed and predicting Lewis structures, or just understanding what you're going to see from Lewis structures over and over again. Note as well that these trends are going to repeat. So the group below carbon, even though carbon is pretty unique and it's the one you're going to see almost all the time, will behave the same way. Nitrogen will behave like phosphorus, which is right below it, and so that's going to have this similar theme. Oxygen, sulfur are going to behave the same, and fluorine in the halogen group, second from the end, fluorine, chlorine, bromine, iodine, these are all going to behave the same, and they will actually come up quite a bit. When you see a halogen, it only wants 1 more electron. It likes to form 1 bond, leaving 3 lone pairs. And finally, you may see out there, and this is a bit beyond the course, but if you do see structures that do not obey the octet rule, that's not wrong. Octet sometimes is simply not possible, but what always must be adhered to is the total number of electrons. Fluorine brings 7 valence electrons. When you write your depiction of something containing fluorine, it's brought 7 electrons. They've got to be accounted for on your final diagram.